Welcome to this movie on statistical mechanics. My name is Jos Thijssen and I have made this movie for my students who I teach advanced statistical mechanics at the Delft University of Technology in the Netherlands. This movie deals with the Wilson and Fisher Epsilon expansion, which starts with a renormalization procedure carried out for the Landau Ginzburg Hamiltonian. In order to appreciate this movie, it's really essential to know what the Landau Ginzburg Hamiltonian is, and in particular it's very important to have studied the renormalization of the Gaussian model, and I have made videos on both topics. The Wilson Epsilon expansion has given extremely good results for the critical exponents in 3 dimensions and even good values for 2 dimensions. And it's therefore one of the great achievements of physics, and it is a kind of culmination point of the research in critical phenomena. In fact, for 2-dimensional models there was an additional development which took place primarily in the 80s with the discovery that critical systems are conformally invariant, but that will be outside the scope of this movie, which will restrict itself to the Wilson Epsilon expansion, and I hope that you enjoy the movie and can learn something from it. We want to renormalize the full Landau Ginzburg Hamiltonian, which contains 3 terms. The first term is a term which describes the variations in the order parameter. You can consider that like a magnetization in the Eigen model. It's x and it's a scalar order parameter. And then there are 2 terms, and they give a potential, and this potential has 2 minima, one for positive and one for a negative value. If R0 is negative, for R0 positive there is only 1 minimum, and that is at x is 0. The first 2 terms in this Hamiltonian constitute the Gaussian model, and in a previous movie I have extensively described the renormalization of the Gaussian model, and so what is new in this case is the 4-point interaction, and that will be the main difficulty now. In the Gaussian model we can carry out almost all the integrals analytically because they are Gaussian. If there is a 4th order term, suddenly the analysis becomes a lot more difficult. And what we need to do is, well, in the Gaussian model we took the first 2 terms and formulated those in reciprocal space by Fourier Transform. And so first we will Fourier Transform this 4-point term, 4th power term, in x. Here is this Fourier transform. So we have a product of 4 x's, and each of those x's is Fourier transformed, and so we get 4xq's, and there is a Fourier factor e to the power iq times r for each of those x's. For each of those x's the r is the same, so we have only 1 r, we have 4 q's, and if we perform the sum over r, we can use the fact that we obtain an n times the delta function q1 plus etc. q4, and if we plug that into this expression, this exponent here disappears because we have summed over it and replaced it by a delta function, and the result is this expression here. And the delta function represents momentum conservation because the q's in a quantum mechanical language, they represent momentum, and the sum of the q's being 0 guarantees momentum conservation for this term. We then have the Hamiltonian in its full Fourier transformed form. These are the terms that we have already encountered in the discussion of the Gaussian model, and this is the term we just derived for the 4-point term. And because the Gaussian model can be treated largely analytically, it can be used as a kind of reference Hamiltonian, a kind of unperturbed Hamiltonian. That's the Gaussian Hamiltonian, and the rest, the term with u and 4 x's on board, is considered to be a perturbation, and we denote that by v. We proceed by carrying out step 1 of the renormalization procedure, which means integrating over all the xq's which have a q that lies inside the interior part of the Brillouin zone. So the Brillouin zone for the lattice is this square here, it runs each component of the vectors inside the Brillouin zone run up to pi. Then in the rescaled model we only retain the q's up to pi over b, and the region in between pi over b and b, that is the red shaded area, and we integrate over all the x's that have a q inside this red shaded area. B is the rescaling length. In fact, in the lattice model it would mean that the lattice constant will grow by a factor of b in the renormalization procedure. The Hamiltonian in the exponent can then be written as hg plus v, just as we have seen a second ago, hg plus v, and we denote the red shaded area, so the q's which have components between pi over b and b, by bb in order to avoid complicated notation. Because v is considered to be a perturbation, it makes sense to expand the v in the exponent, and then we have here the first three terms of the Taylor expansion of e to the power minus v in this expression. Now we note that, for example, this term where we have v in this integral resembles the numerator of an expectation value. And so we write this term as the expectation value of v, and we multiply it by e to the power minus h prime g. And here you can see the proper definitions of the expectation value. So we take the term here, e to the power minus hg, with the v. We integrate over the xq's in the Brillouin zone, and obviously if it would be a genuine expectation value, we need to integrate over all the xq's where q fills the entire Brillouin zone. This is only a part of the Brillouin zone, and here we have the appropriate normalization. Normally this is a partition function. This is a partition function which pertains only to the q's that lie in this bb zone, and this partition function is called e to the power minus h primed g. The reason for this notation is that the q's that lie in the interior part of the Brillouin zone, so not in bb, they will survive, and so this expression, even after the integration over a part of the xq's, is still Gaussian in character for the rest of the xq's. And then in this expression we see that we have added here, by putting these brackets, this extra denominator, this kind of partition function, e to the power minus h prime g, and we compensate for that by multiplying the expansion by e to the power minus h primed g. We then proceed by writing the result, e to the power minus h primed, in the form of e to the power minus a Gaussian Hamiltonian primed. That's this Gaussian Hamiltonian primed here, minus a new perturbation v primed. So that means that in this expression, all these terms, they represent the part e to the power minus v primed. So e to the power minus v primed is the expression that we have here on this right hand side, where we have a Gaussian expectation value everywhere where there are angular brackets. Now, in order to find v primed explicitly, we take then the logarithm on both sides. So here we have a minus v primed, and on the right hand side we have a logarithm of 1 minus etc. And the perturbation terms, v and v squared, all the remaining terms are called x. X is a small parameter, and so we now perform a Taylor expansion of the logarithm in order to find a systematic approximation, a systematic expansion of v primed in terms of the powers of v inside the expectation values. Performing the Taylor expansion of the logarithm is straightforward. We do the round logarithm of 1, which itself is 0, so the first term is proportional to x, and then we have minus x squared over 2, and then we have higher order terms. And using that, we obtain v primed is the expectation value, the Gaussian expectation value of v minus 1/2, the Gaussian expectation value of v squared minus v Gaussian expectation value squared. So this is the variance of v within the Gaussian expectation value. This is an expansion which occurs extremely often when we do perturbation theory in statistical mechanics. So there is a special correction always that we do not see the expectation value of the perturbative quantity itself squared, but we always have this term minus v squared, and we have similar compensating terms in the higher orders. This expansion occurs so often that it has a special name. It's called the cumulant expansion. Next, we need to calculate all these Gaussian expectation values. So let's see what the Gaussian expectation value of v gives us. Recall that v was the term which contained 4 x's. So here we have xq1, xq2, xq3, xq4, and we calculate this Gaussian expectation value. So here it is. In the Hamiltonian we only have the Gaussian terms, and this is the expression we want to take the expectation value of. Now, in the analysis of Gaussian expectation values in the video on the Gaussian model, we have seen that the term here in the exponent causes the expression here to factorize. The exponent factorizes into pairs q minus q, so only expectation values where we see a pair of q and minus q, they survive. So the first thing we could do is find pairs q minus q, q minus q. We can find 2 pairs among the 4 x's which both have opposite q. So we have a pair xq, x minus q, and another pair xq primed, x minus q primed. And we know for both, because this exponent factorizes, that we know the expectation value, and they are independent for both pairs, because we just have this factorized probability factor there. So the first pair gives us a 1 over q squared plus r0, and the second pair gives us 1 over q primed squared plus r0. And the next step is then, of course, to work out in how many ways we can find these 2 pairs. But we should also consider the case where the 2 are the same. The q is equal to the q primed. That is calculated here. So here we see again the same probability factor Gaussian. And now we have 2 pairs where the q and the q minus q are the same for both pairs. And if I calculate this integral, it can be done straightforwardly. It gives me a 2 divided by r0 plus q squared squared. So in summary, if we have 2 distinct pairs, we have this expression 1 over q squared plus r0, 1 over q primed squared plus r0. If we have 2 identical pairs, we have this term here. And we can summarize these results in the form of Wick's theorem. Wick's theorem states the following: if we have 4 x fields here, then we should always identify pairs of x which are opposite, because otherwise the expectation values of the pairs would vanish. So we divide this up into pairs, and we can do that in 3 ways. We have either the pair q1, q2 together with 3 and 4, or we have 1, 3 and 2, 4, or we have 1, 4 and 2, 3. And those are then the combinations that we can make of those pairs, and Wick's theorem tells us that all the ways in which we can divide up the x's in pairs, if we put them in the expression here, that gives us in fact this expectation value. And we can check that now. So suppose that we would have the situation where we have in this sequence here a pair with q and minus q, and we have another pair with q primed and minus q primed, where the q primed is not equal to q. In that case, we can only have an expectation value for this one times the appropriate expectation value for this pair, and indeed that will only this term will give us a contribution, this one with a q minus q combination and that one with a q primed minus q primed combination. And all the other ways in which you can find, for example, this could be a q and that could be the minus q, this one the q primed, this one the minus q primed. In that case it would be this term, which gives us the only non-zero contribution. So let us now look at the situation that we just analyzed, where the q is equal to q primed. So then we have, for example, a q minus q, q minus q. In that case, we could combine the xq1 with the xq2, so that would form this pair here. But we could also, because the q4 is the same minus q, we could combine xq1 with x4, and that's the last combination. This one would in that case vanish, and so we have 2 times the square of the individual expectation values, and that matches precisely this expression here. So Wick's theorem can always be used. It says that if you have a sequence of x's here and you want to take the Gaussian expectation value, it's important that this is a Gaussian expectation value, then you find all the pairwise partitions of these x's, so you extract all the pairs. It can only be done if you have an even number of x's, and then you put all those combinations on the right hand side, and for each pair you take the expectation value. It's important to note that this always preserves the momentum conservation, and that's because in each pair we need to have a q minus q combination, and so each pair individually guarantees momentum conservation, and therefore the entire expectation value guarantees this conservation. After this intermezzo, we return to the calculation of the expectation value of v, which contains 4 x's, and we need to integrate over only those over the x's with q's inside the red shaded area. So it is not guaranteed beforehand that we are integrating over all 4 x's. It could be that 2 lie inside the interior part and that 2 lie in the BB region, which is the red shaded area here. So let me indicate that this area is the BB area. And so if we see in how many ways we can distribute the x's, or the q's rather, the q's in this over this Brillouin zone, we find 3 cases. Case 1 is the case where all the q's lie in the interior part of the Brillouin zone, so they are outside of the red shaded area, which was called BB. And in that case, as I do not integrate over any of those x's, the v remains completely untouched by taking the averaged, and we still keep all the terms in their original form. So the only aspect which distinguishes this from the original Hamiltonian is that now all the q's need to lie inside this interior part of the Brillouin zone. We can also associate a diagram with this term. This is that diagram. We have 4 outgoing lines, and they all correspond to each of the q's, and of course they should add up to 0 because of the delta function, which expresses momentum conservation. We then turn to case 2, and in case 2 there are 2 q's which are inside the interior part of the Brillouin zone, and there are 2 q's which are in BB, so the outer rim. And we need to, of course, to identify the pair which lies in BB, and we can do that in 6 ways because we have 4 q's. So 4 over 6 over 2, the combination gives us 6 ways. There is also a diagram that we can associate with that, and a mathematical expression, and they correspond 1-to-1 to each other. So if we have identified the 2 q's which lie in the BB zone, then we need to perform the integral over those, and we can do that for each q in that BB zone. And if we take that integral, so we calculate the expectation value of an xq, x minus q pair, then we have this expression here that we have already encountered several times, and the q1 and q2 are in this case chosen to be inside the Brillouin zone. And so the diagram which goes with this is we have 2 outgoing lines. Those are the lines that are not integrated over, and then we have a q which in this case leaves the vertex, so it has a positive sign, and here this same q enters the vertex, so it has a negative sign. So this is just a representation of this mathematical expression. So this is the xq x minus q expectation value, and it corresponds to this loop in the diagram. And it it contains an integral over the q's inside the BB, so the narrow zone. Furthermore, there are an xq1 and an xq2. They are in the anterior part of the Brillouin zone, and because these guys conserve the momentum and all four q should add up to 0, also these should form a pair q primed minus q primed. It's different from the q that we have here. So q1 plus q2 should add up to 0. Finally, we turn to case 3, where all the q's lie inside the red region. So that's BB, the outer rim of the Brillouin zone. And these x's can only survive if they occur in pairs. So we need two pairs in BB, a pair with q and a pair with q primed, and we can partition the four q's in three ways into pairs. And each pair will give me a correlation function 1 over q squared plus r0. So that's what we obtain after taking the integral over the xq's. And we need to do that for each q and for each q primed. So we have the product of an integral or sum over q and a sum over q primed. But they both give the same result. So I can write it as the sum over the BB squared. And the 3 here accounts for the 3 ways in which I can partition the 4 into 2 pairs, and we have of course the prefactor of u over n. Now if we perform this integral over the BB, then we are left with just a number. And so this term just gives us a constant, and it doesn't contain any interaction, and therefore it will not influence anything in the it will not influence the critical behavior as described by the renormalization transformation. So we neglect the term associated with this diagram. This is the diagram which corresponds to this expression. We have a sum over the q, and we have a sum over the q primed, and they are both given by a bubble, and so this is a double loop diagram, but it results because there are no outside lines. We don't have any interaction left in the model, and therefore this is just a number which can be neglected in the renormalization transformation. Now, going back a little bit to recapitulate what we are doing and where we are, we had to calculate the contributions due to different terms in the cumulant expansion. So the first term was the expectation value of v, which occurs here. And we have just gone through 3 different cases depending on which of the q's are inside or outside the central part of the Brillouin zone. So the next job is to calculate the expectation value of v squared, and that's where we will turn to now. So here we are. We calculate the expectation value of v squared, and that is just the product of the q to the 4th term. We have now 8 q's in total. We have q1 to q4 and we have q5 to q8. The first one, the first 4 belong to one interaction, and therefore that has also a delta function on board. And the remaining q's, 5 to 8, those are 4 q's. They are also connected together by a delta function which guarantees the momentum conservation. And in this case we again have to identify which of the q's are inside or outside the central part of the Brillouin zone, the outer part being BB, and we only integrate over the red shaded area, which is BB. And it turns out that we need to distinguish 4 cases. The 4 cases are distinguished by the choice that we make for the QIs that are chosen inside the interior part of the Brillouin zone or in BB, the outer part. And the simplest choice is to take all the q's inside the interior part so that there is not integrated over them. And in that case, we are just left with the original interaction, which we represent by these two vertices. There is nothing which we integrate over, so there are no loops, no connections between the two vertices. And the weight of this contribution is given by, for each vertex, we have a u over n, and we have a delta function for each vertex, and so that immediately gives us back the original term. Let us then move to case 2, where we choose 2 qi's inside the BB, which is the outer part of the Brillouin zone, and the remaining 6 are chosen inside. Now remember that all these q's are grouped into 2 categories. One is the q1 to q4, they are linked by a delta function, and we have the q5 up to q8 also linked by a delta function. And of course it makes a difference whether we take the 2 fat crosses that we have here, whether we take those from the same group or we take them from a different group. And before we proceed, it is important to note that these 2 fat crosses should be opposite, because they will be contracted by the integration over the xq, and then we need q is equal to minus q primed, as we have seen very often already. Case 2a is the one where we take 2 q's in BB from one and the same group. So we take in the left group, we take 2 q's to be the same. Then we have an incoming, we have 2 outgoing lines. Those are the ones that are not contracted. So they are contracted when they are in BB because they form a pair, which necessarily is an opposite. So the pair that is integrated over is represented here by this loop. It should be q and minus q, and because of overall momentum conservation at this vertex, the remaining outgoing legs should also be opposite. And then we have in addition the second group, which is completely unchanged. When we work out the mathematical expression corresponding to this diagram, we need to realize first that taking 2 out of 4 can be done in 6 ways, and we can take them either from the left group or from the right group, so we have to multiply that by 2. There is a minus sign due to the cumulant expansion, which has a minus sign for the second order term. There is a u over n squared because we have 2 vertices, and then there are these 6 x's, and here is the integral over the loop, which, because these points are chosen inside BB, gives us an integral over, or sum of q inside BB of 1 over r0 plus q squared. Furthermore, there are delta functions. There is a delta function for q1 plus q2, which tells us that these should be opposite too, and in that case I take those to be these ones. And then there is a conservation of momentum at the second vertex, q3 up to q6. And now we realize that there is another term in the cumulant expansion, which is the expectation value of v squared. And when we worked out a single expectation value of v, we have come across both this loop diagram and this vertex diagram. And so that means that this combination will also pop up in this term, and if you work out the math, it turns out that in the end all the disconnect diagrams disappear. So this configuration with a minus sign due to the second term compensates the occurrence of this term due to v squared here. And that happens at all levels. That's a very general feature that you find in these diagrammatic perturbation theories. Only the connected diagrams survive. Now we consider case 2b, and in case 2b we take 2 q's from different groups, so one here and one there, and we can draw an arrow, so that means that this one is plus q, that one is minus q. That occurs because we integrate over the xq's, and that fixes this condition. A q and a minus q should always be paired. And then the remaining q's are outgoing lines of this diagram. If we consider a term of this form, it has 6 x's in the Hamiltonian, and such a term was not present in the original form of the Hamiltonian. It turns out that this contribution corresponds to an irrelevant operator in the end, so that's a reason why we are not considering this diagram further, because we know, and I will not show that in detail in this movie, but it is known that such a diagram corresponds to an irrelevant diagram. So after discarding that diagram, we move to the next choice, which means that we take 2 pairs of q's inside the BB. We have a pair q minus q, and we have a pair q primed minus q primed. So instead of 4 fat crosses in BB, we have now 4 fat crosses. And we consider now the diagram which corresponds to this choice. Again, we have 2 options. We can either take the pair from this pair from one group and this pair from the other group, and that is represented in the diagrams here. So we take q1 to q4, and we link 2 of the q's in a loop, and we also take q7 and q8, and we link those 2, and then there are 4 outgoing legs left. But similar to the argument that we have given above for this diagram, which was disconnected, and therefore this term cancels the contributions that we find here, we also find that this term will be cancelled. It's disconnected, and therefore we neglect it from now on. The next case, 3b, is very important. In that case, we take the q from the left group and the minus q from the right group, and likewise for the q primed. So we have a q here from the left group which enters then the right group. We have a q primed from the left group which enters the right group, and we find that this is an outgoing arrow, this is an incoming arrow, so that corresponds to this one being at that vertex. It is plus q, and this one is a minus q, and it's likewise for the q primes. And so all in all, we should always satisfy the momentum conservation at each vertex, and because the q and the minus q cancel, the q primed and the minus q cancel, the q1, q2, q3 and q4 should also cancel. In how many ways can we make this diagram? Well, we have to choose the 2 which are not contracted here, so 2 out of 4. We can do that in 6 ways. On the right hand side we can also do that in 6 ways. But then there are 2 ways in which we can connect the left part to the right part, because we can connect this one to this q, or we can connect this one to the other q, and then so we in a sense we take this red dashed line and we could mirror the left vertex with respect to that dashed line. We get a different topology leading to the same expression. So in total, because of these 2 ways to connect the left and right vertex, we have not 36, which would be 6 times 6, but we have an additional factor of 2 because of that connection. Let's now consider the momentum conservation in a bit more detail. At the left vertex we should satisfy momentum conservation, and because all the lines are outgoing, each momentum has a plus sign, and that should add up to 0, so q1 plus q2 is minus q primed. On the right hand side we have 2 incoming lines, so they have a minus sign, and then we have q3 and q4, and that's why this is finally the momentum conservation for the right vertex. And if we add these 2, then we see that on the right hand side we get a 0, and on the left hand side we get a delta function for q1 plus q2 plus q3 plus q4. So we end up with the following expression. We get a minus 1/2. That is due to the cumulant expansion. We have the u over n squared because we have 2 vertices. We have 72, that's the combinatorial factor that we worked out. We have xq1 up to q4, that are the 4 outgoing lines. And then for the interior we have an integral of q, a sum of q inside BB. And this pair here gives us a 1 over r0 plus q squared. Now the second pair is not independent. We do not have an independent sum over the q primed, because the q and the q primed are linked. Once we know the q1 and the q2, then we know the q, then we also know the q primed. So for the q primed, we have this value here. It's q1 plus q2 plus q. And that's why we have only a single sum over q, but we have two terms, and the second looks quite complicated. Then we have this delta function that, as announced, arises from the individual individual momentum conservations at the two vertices. And we note that the form of this term is exactly like the form of the 4-point interaction in the original Hamiltonian. That was a u times 4 of these x's, and there was indeed a delta function. Note that this integral just gives us a number, and so that doesn't change the form of the interaction. It's just a prefactor in which this is incorporated. And therefore we say that this term renormalizes the 4-point interaction. It changes the prefactor of the 4-point interaction because we need to add this term to the 4-point interaction in order to get the new Hamiltonian after renormalization. We move on to case 4, which corresponds to taking 3 pairs of opposite q's in the BB, in the outer rim, and we can either take 2 from the same group and then 2 pairs from the other one, and that leads to a disconnected diagram, and by now we know that all these disconnected diagrams vanish, and so we won't consider this any further. However, the other case with 3 pairs is important. In that case, we connect 3 q's from one side to 3 q's from the other side, and we obtain this diagram, which has 2 xq's apart from integrals. So we have an xq1 and we have an xq2. So that's a 2-point interaction, which contributes to the Gaussian interaction term. In how many ways can we connect the left side to the right side? Well, first of all, we have to choose one q to be not in BB, and we can do that in 4 ways. We can do the same on the other side, also 4 ways, and then we can connect these 3 to the 3 branches coming out here, and because there are 6 permutations of 3, we can do that in 3 different ways. Furthermore, there are the usual minus 1/2 and the u over n squared. And then we have a complicated integral involving the q primed, and the q primed. Well, in fact, the q primed is again not independent from the q and the q primed, but in this case we have a double integral. A double integral 1 over q and 1 over q primed. However, in the end it will turn out that this diagram doesn't give a contribution, and the simple argument at this stage is that we have a double integral. We have an integral over q and q primed, and both integrals are over the outer part of the Brillouin zone, which is BB. Now BB is a small region. It's a narrow region. In fact, its width is given by b minus 1, and therefore if we have 2 such regions, it scales with b minus 1. If we can of course, we have some freedom in taking the b. If we take it close to 1, we can make this term arbitrarily small. So that's a simple argument to see why this term cannot really contribute to the physics that we are after. In the end, there is a more subtle argument, but I will not go into that here. Anyhow, this diagram, this contribution to the 2-point interaction, turns out to be not relevant in the end for our analysis, and so I leave it out here. Time to summarize. So we have performed one step of the renormalization procedure, step number 1, which consists of integrating out all the xq's in this red area. And what have we obtained? Well, first of all, we obviously have the 2-point interaction, which just survives for all the q's that are not inside the red region. So here everything is kept the same. So in particular, the 2-point interaction term, we see that coming back unchanged. The first order cumulant term has led to a term corresponding to this diagram, which also has an incoming and an outgoing line, Q1 and Q2. As you can see here, due to momentum conservation, there is a delta function, so the Q1 should be opposite to the Q2. And this loop gives an integral over the correlation function that you can see here. Now, I have already mentioned before that the integral is only over this narrow region, and if b gets close to 1, this region gets narrower and narrower. And moreover, if we transform this sum to an integral, we see that it scales with the number of lattice points, that's n. And so we call this number, this integral, we call it NA, and we note that it's proportional to b minus 1. But the name that we give to this is NA, and this n then nicely cancels against this n. But it's an n which really indicates the scaling of this integral with the number of lattice points. We then have another first order term, which is just the original 4-point interaction in the case where the 4 q's were lying in the central region of the Brillouin zone. And so they were not integrated over, and this term therefore keeps its original form. Then we have the last term, which comes from the second order cumulant expansion. It's a connected diagram, obviously, because otherwise it would not survive. And it contains an integral over a q in the interior loop. Well, on the other side we should have a q primed, and then there are outgoing lines q1, q2, q3, q4, and we have checked extensively that the total momentum on the outgoing lines should be conserved. Not surprising, because the two individual vertices guarantee momentum conservation. And there is a prefactor 36 due to combinatorics, and there is a u over n squared due to the fact that we have two vertices here. And there is this complicated integral, which has a term 1 over r0 plus q squared, and there is a term r0 plus q1 plus q2 plus q squared. And so we will now look at what we can do with that complicated integral. Because the q1 and the q2 lie in the interior part of the Brillouin zone and q lies in the rim, we try a Taylor expansion of this term and the integrand with respect to q1 plus q2. So we do the Taylor expansion with respect to the sum of q1 plus q2. And all the q's here should be vectors. And if I perform that Taylor expansion, then we see that the first order term is proportional to q, and this one is even in q, and therefore it's antisymmetric in q. And because the BB, that's the outer part of the Brillouin zone, because that is usually symmetric, this term will cancel in the integral due to antisymmetry. And then we have a term which is proportional to q1 plus q2 squared. So that means that of the q1 and the q2 we will see derivatives, because a q represents a derivative in real space. And so these terms that correspond to the second order contribution of the Taylor expansion, they have the form gradient x squared and then x squared. These terms turn out to be irrelevant. They give us eigenvalues that are irrelevant and therefore do not affect the critical behavior, and therefore we just leave them out. And if we leave out this q1 plus q2, then this integrand gets a much more simple form. It's 1 over r0 plus q squared, because we neglect the q1 plus q2 term here. Now the integral here over the q in BB, that is again an integral which scales with the number of lattice points. That was Ln, and so we call this NB, and because it's only over the outer part of the Brillouin zone, also this term, just like the previous one that we defined, the NA, is proportional to b minus 1. Let us now consider the first two terms. So we see that we have a term which is not changed. Of course, the q squared is somehow outside of the renormalization procedure because it's not affected. But the r0 term is changed because here we see also a term with an xq, x minus q. Recall that that q1 is opposite to q2. And therefore, these prefactors, the NA and the minus 6u over n, they give an extra contribution to the R0, which is a result of the first step of the renormalization procedure. Due to our different definition of a for the integral that we had in that expression, it acquires a very simple form. R0 primed is R0 plus 12ua. Going back to the equation, we can still check that. So we should have the 1/2. So this term should acquire a factor of 12. 12 times u over n. And the n is compensated by this. And we have the a and we have the u here. So that gives rise to this equation. R0 primed is R0 plus 12ua. And that is the equation which describes what happens in the first step of the renormalization transformation. Here we see again the two four-point contributions. This one is the original interaction, which comes from the first order cumulant, where we have chosen all the q's inside the interior part of the Brillouin zone. And this is the term which gives us the bubble diagram. And it has 4 outgoing legs, so it renormalizes this term by adding a small extra contribution. Obviously here the qi's, just like in this sum, they should all be outside of the b, which is the small part near the edge of the Brillouin zone. So the qi's are all not allowed to lie in bb. So after this step, the Hamiltonian has the following form, where we see two differences with respect to the original Hamiltonian. The first one is that all the sums over the momenta are now restricted to the interior part of the Brillouin zone. So it should always, all the components should always be smaller than pi over b. Otherwise, they have been integrated over and incorporated in the constants which enter in the R0 primed. That's a second change. So this parameter has changed to R0 primed. And the parameter for the fourth order term also has changed. It is now u primed. The second step is then to rescale the qi's so that they fill again the original Brillouin zone. So I need to transform this q here into a b times q. And we do that by introducing a new qi primed, which is b times qi. In fact, the entire renormalization procedure boils down to change to a rescaling of the lattice constant. So the lattice constant has increased by a factor of b, and that affects this term n here. This number n represents the number of lattice sites. And if we change the lattice constant from 1 to b, and that's what we effectively do in the renormalization procedure, then the new number of lattice sites, n primed, is the old number divided by b to the power d. And so we should take that into account. We would like to have a consistent formulation here, so we should have an n primed here. And therefore we need to replace this n by an n primed, which is related to n in this way. So performing this second step, the qi primes, they fill now the entire Brillouin zone, so that's what we need. We pay a price for that because this q is now a q primed divided by b, and therefore the prefactor of the q prime term is no longer 1/2, and we are going to fix that by rescaling the x. We are integrating over x, so rescaling doesn't matter. And if we rescale the x by a factor of lambda, we have a lambda squared entering here in the Hamiltonian. And furthermore, we have now an x which depended on q, and q is q prime divided by b. But we relabel the x's and we call them now x tilde. So x tilde is just the function of q, and it is the same field as x of q primed over b. Then here we have replaced the n by the n primed. That gives me a factor of b to the power minus d. And in this term we have 4 x's which are all rescaled, because we rescale all the x's in the same way, and therefore we have a factor of lambda to the 4th. And this q obviously runs over the entire Brillouin zone. If we want to restore the prefactor of 1/2 in front of the q primed, then that is possible if we take lambda equal to b. Furthermore, the q primed is summed over, so we can call it q again, and the x tilde will be integrated over, and we call that x. It will be integrated over in the partition function, and so we are left with a Hamiltonian which has almost exactly the form of the previous one, of the original one, except that there is now an R0 primed here, which is multiplied moreover by the b squared. This term is exactly the same as it should, and the 4-point term acquires a factor of b to the power 4 minus d, and it has a u primed here instead of a u. Recalling the values of R0 primed and U primed, which arose from the first step in the renormalization procedure, we can see what are the additional changes. So a b squared in front of the R0, a b to the power 4 minus d in front of the U, and then we have these extra terms. This one also, of course, acquires this factor b squared, and this one is just the 36u squared b that we see here. Having this renormalization transformation, the first thing we should look out for is a fixed point, and there is a trivial fixed point at R0 is u is 0. Obviously, when we put zeros here on the right hand side, we will have a 0 on the left hand side. It's a point at which the Hamiltonian, however, is not 0, because always we have this term with a half q squared, which is the Gaussian model at R0 is 0, and that represents a critical phase. So it's a fixed point representing a genuine critical phase. And obviously, once we have the fixed point, the next step in renormalization is to look for the eigenvalues of the linear transformation and to search for the scaling dimensions. And to do so, we consider u and r deviating a little bit from 0. So u and r are both very small, and so we make an expansion of the right hand side, and then the linear terms in u and r0, they give us the matrix A that we need to diagonalize, and that describes the renormalization transformation close to the fixed point. So first of all we have this term here, the r primed 0 dr0, that arises from this one, gives us a b squared. Then there is a dr0 primed du, that's this term, which gives 12a times b squared. Here there is a 0 because there's no derivative, there's no dependence of u primed on the r0. And the remaining terms give us this, but obviously we need to take the derivative at the fixed point where u is 0, so this second term doesn't play a role. So we have an upper triangular matrix, and we need to find the eigenvalues. The first eigenvector is 1, 0, it's easy to find, and its eigenvalue corresponds to the upper left element, which is b squared. Lambda, the eigenvalue, should have the form b to the power z, and z is the scaling dimension, and we have found that the scaling dimension is 2. So just as in the case of the Landau Ginzburg theory, we find that the critical exponent for the correlation length nu, which is given by 1 over z, is 1/2. And that means that the scaling, because the z is larger than 0, it's a relevant operator. So it also tells you this is the eigenvector which has a component along the r0 direction, so the first element here is r0. And so in that direction, if we change the temperature, then we change r0, and in that direction this fixed point is repulsive. If we walk away from the critical temperature, then the renormalization flow will drive us away, and the corresponding critical exponent is 2 for the scaling dimension, and nu therefore is 1/2. The other critical exponent corresponds to this as a strong component in the second variable, that's u, and also a small one in the first one, so that is due to this term here, which typically is very small, so it's primarily in the direction of u. And we see that the eigenvalue, if you work it out, it's primarily b to the power minus 4 minus d. And that is very interesting, because now we see that if d is smaller than 4, then this is a positive exponent and the eigenvalue is relevant. If it's larger than 4, then this eigenvalue is irrelevant. Now this corresponds to the fourth order term, so the fourth order term, the fourth point term in the Hamiltonian, is relevant only at dimensions smaller than 4. And so this is again an example where we see that the critical behavior for d greater than 4 is usually trivial. It's governed by the Gaussian fixed point. For d smaller than 4, there is something else going on, and so that is what we shall address now. Here is a cartoon of the flow. We have a fixed point at r0 and u being 0. That's the central point. There is a relevant direction along r0, so if we deviate from the temperature at which the system is critical, we walk away. And there is also a attractive direction for d greater than 4, and that is more or less along u, so that could be a direction like this. And so the flow should be like this. In the other case, we have the same fixed point. In fact, in this case, the flow along r is repulsive, so it's a relevant direction. And also the flow along the other eigenvector is relevant. And so in all directions, this fixed point is repulsive. So typically, if we have the choice, we would walk away from this fixed point and go to some other fixed point, which may be at u is infinity, or perhaps at a finite u. It turns out that there is indeed a fixed point at a finite value of u, and we can find that by taking our renormalization equations, which I've copied here, and instead of having an r0 prime primed on the left hand side and a u prime primed, I now have the same value here as I have there, because I want to solve for this fixed point. And the second equation is the simplest to start with, because it only depends on the u star and it does not depend on the r0 star. So we can solve that equation, and it gives us u star is b to the power 4 minus d minus 1 divided by 36b to the exponent 4 minus d, and then capital B, which is just a number because that was an integral that we evaluated. Now there's one thing clear here. If the dimension is 4, we see that u star is 0, and that makes sense because there is no finite u point for d beyond 4, and so u star should vanish precisely when d is 4. Now let's work out the r star. We can do that now because we know what u star is from the second equation. We plug it into the first one, and what we obtain is this expression, and that involves a and b as a quotient. Here I've made two plots for the renormalization equations, and what I've done is I've estimated the values of a and b. Those are these integrals as follows. It is a sum over q in bb. bb is a small region which is near the edge of the Brillouin zone. I have assumed that the Brillouin zone is spherical, and so I've just plugged in the value of pi for q, and therefore I get here an r0 plus pi squared. Then the integral is over the surface, and that scales with q to the power of d minus 1. I've substituted pi again for q, and then the width of the shell which represents this BD, the width of that shell, I've emphasized that already before, is B minus 1. And so I have used these values for D is 5 in this case and D is 3 in that case. And then I've just run these renormalization equations. And indeed we see that in this case there is a attractive direction. The points on this line, they all move towards the fixed point, which is here. And if I walk away in this direction, then we see that the flow is repulsive. Well, the arrows are not terribly big, but I hope that the idea is clear. In this case, this direction is repulsive, so we walk away in this direction, and then we end up at the new fixed point, which I indicated here by the red star. So this is the point U star, R0 star, and we see that we find those at finite values away from the fixed point at 0, 0. What we have done so far is performed a perturbative analysis in terms of U. So U better be small for our analysis to be valid. And in fact we have seen that U is 0 when the dimension is 4. And so when the dimension deviates a little bit from 4, we have a small value for U. If the dimension is, for example, 2, we are far away from 4, and then U will become very big. And so our analysis should definitely not be very accurate. And we can now exploit this notion that we want systematically to expand in U. In fact, we see that that U is coupled to 4 minus D, and therefore we introduce an expansion parameter, which is epsilon. It's defined as 4 minus D, and we do that following Wilson and Fisher in 1974. And this expansion is known under the name epsilon expansion. Here I've copied my renormalization equations. I've not changed anything except that I have now given a single prime to the R0 and the U primed, although these are the ones which have the B on board. Previously I called those double primed, but there was no point in doing that. And here are the fixed point values that we have found before, and I have now simply replaced the 4 minus D by an epsilon in the renormalization equation here, the second one, and also in the values for U star and R0 star. And if we want to expand everything to first order an epsilon, we will systematically replace a B to the power epsilon by a 1 plus epsilon ln B. So if we do that with our U star, we see that it has this particular form, and we can write it as epsilon ln B divided by 36b. And now you may be worried because it seems that the value of the fixed point depends very strongly on B, and obviously we would not like the fixed point to depend on the rescaling length that we have shown. Well, to first order indeed that is not the case, because the ln B that scales B is close to 1, so the ln B scales as B minus 1. It's approximately B minus 1, and this B in the denominator was an integral over the outer part of the Brillouin zone, and the width of that part was also B minus 1, scaled as B minus 1. So we see that the B minus 1 dependence cancels in the numerator and the denominator. And if we play the same game for the parameter R star, we find that it's minus epsilon over 6 A over B. Just as in the case of the Gaussian fixed point, we now need to linearize around the critical point, so the new fixed point. The new fixed point is U star, R0 star. They are both finite values. We deviate a little bit from those, and then we perform the renormalization transformation, and we end up close again to the fixed point, but at different positions described by delta U primed and delta R0 primed. And so we consider now the relation between the delta U primed and the delta U, and the renormalization transformation, just for your information, I have copied those again here. So let's see what we get in that case. It's rather straightforward. If we change this U by a small amount delta U, what are the terms and we change also the R0 by a small amount delta R0. What is then the change in this U primed? So that is the delta U primed. Well, first of all, we get a delta U multiplied by B to the power epsilon. And then, because there is a term U squared here, we have 2 times U star times delta U multiplied by B to the power epsilon B. And then there is a term which is important not to forget. The B obviously is the integral over the correlation function, but the correlation function depends on R0. And so this term depends on R0. If we shift on the R0 by an amount delta R0, we have an extra contribution which is proportional to the derivative of B with respect to R0, then multiplied by R0. And I have already indicated here that this term is order epsilon squared. Why? Well, it scales with U star squared, and U star scales with epsilon itself. So we can safely neglect this term because it's second order in epsilon and our analysis is strictly first order in epsilon. So we have this expansion which contains the factor U star. We know what U star is, we have found it before, and if we plug that in, it's very nice. This 72 over 36 gives us a 2, and the B, the capital B, cancels against this one. So these two terms, they now yield these simple 2 terms. And we see that delta U primed is just proportional to delta U. Then we move on with delta R0 primed. If we take again the equations and work that out, we see obviously a delta R0 times B squared. Then there is a term with delta U arising from this term, and just like in the case of B, we have an additional term dA dR0, because A depends on the parameter R0, multiplied by delta R0, and then B squared U star. And here is only a single U star, so this term is proportional to epsilon. So let us recall now what A is and what B is. NA was defined as the sum over the Q in the small outer part of the Brillouin zone of 1 over Q squared plus R0. And NB was almost the same, except that it had a square here in the denominator. And if we compare these two expressions, it's immediately clear that the dA dR0 is minus B. So we can replace this dA dR0 by minus B. And that's fortunate because the U star has a B in the denominator, and that would then cancel against this B. So we can get rid of the A and B dependence in this term. However, this one will remain. Indeed, if we use this, the fact that dA dR0 is minus B, and we use the specific form of U star that we know, then we obtain this simple equation for delta R0 primed. It has 2 terms that are proportional to R0, and there is a contribution which is proportional to delta U. So in summary, we have obtained the 2 following linearized equations. Delta U primed is given by this expression. It's just proportional to delta U, and the delta R0 primed has a part which is proportional to R0 primed, and a part which is proportional to delta U, and therefore we can now immediately write down the matrix which describes this linear transformation between the delta U and the delta R0 on one hand, and the delta U primed and the delta R0 primed on the other. This is the matrix that we obtain, and just like in the case of the Gaussian model, we can immediately read off the eigenvalues. They are these 2 elements. This upper left element and this lower right element. So let's see what they tell us. The eigenvalue corresponding to changing R0 and therefore changing the temperature, that's the thermal eigenvalue, is B squared minus epsilon over 3 times LMB. And to first order an epsilon, we can write this as B to the power 2 minus epsilon over 3. The remaining terms are then order epsilon squared, and therefore we have a exponent, a scaling dimension here, z, which is 2 minus epsilon over 3. and in dimension 3 the epsilon is taken to be 1, and so it's 5/3. The other eigenvalue, on the lower right, that can be written, that is simply b to the power epsilon times 1 minus 2 epsilon ln b, and that has the form b to the power minus epsilon up to order epsilon squared. And because b is greater than 1, this is an irrelevant eigenvalue because the lambda u is smaller than 1. And therefore the critical behavior is determined only by this z. So let us analyze what we have ended up with. The nu is the critical exponent for the correlation length. It's 1/z. And if we take epsilon equals 1, this was 5/3, so then we get a value of 0.6. Now many authors do this differently. They write, okay, we have 2 minus epsilon over 3, the exponent is 1/2 minus epsilon over 3, and if we expand this to first order and epsilon, we get a half plus epsilon over 12, and that is 0.583. So the difference is due to the way you approximate the result, and it's always of order epsilon squared. Although epsilon is 1 here, it's the prefactor of the epsilon squared term, which is also very small. And this is the result, which is in fact not so bad if you realize that the experimental value is between 0.6 and 0.7. So you may be tempted to improve on this, to go to higher order and epsilons. It's very hard, it's a lot of bookkeeping, and people have carried out these expansions up to 5th order and considered all kinds of asymptotic expansions. And the best value that people have come up with so far is 0.631, which is way better than the experimental accuracy. And the same holds for the other exponents. In fact, we have now only considered a thermal exponent. If you also want to analyze the magnetic exponents, you need to apply a field in the Hamiltonian. In fact, that's possible. I've now done that here because I thought the analysis was already sufficiently complicated. But it can be done, and then you get the values for all the exponents, and they are always invariably very accurate, better accuracy than the best experiments. Another thing that you could do is to look at models where the x is a bit more complicated. So what I have done so far is looked at scalar fields, so the x is just a scalar. You can, however, imagine that you have a model in which the degrees of freedom are, for example, vectors in the plane. Then there are 2 components to this x. Well, in fact, 1 component if you only consider, obviously, the angle theta, but you can imagine that there are many models in which the order parameter is really has more than 1 dimension. In that case, the generalization of what we have done is rather straightforward, and it's often done in the analysis right away. I have refrained from that in order to avoid this complication. The result that you obtain is for the nu is this. It's 1/2 plus 1/4 and an n plus 2 over n plus 8 epsilon. If you put in n is 1, you get 3/9. So you get 1/12 times epsilon, and that matches the result that we had. And of course it should be like that. So all in all, the epsilon expansion is very powerful. It has given excellent values for the critical exponents, and it's one of the great achievements of theoretical physics in the end of the 20th century.